Well, we're going to work another problem here and try to use our mechanical energy and combine with a non-conservative force in order to figure out the maximum height reached by a stone when we have a drag force on it. So I'll just read the problem. A stone with weight of 5.29 newtons is launched vertically from ground level with an initial speed of 20.0 meters per second, and the air drag on it is 0.265 newtons. Throughout the flight, what are A, the maximum height reached by the stone, and B, its speed just before it hits the ground? So, let's continue with our mechanical energy and tacking on a non-conservative force times a distance to make it a work function. So with this problem, we start mgh initial, that's equals 0, plus 1/2 m. V is 20 meters per second. 20 meters per second squared is going to equal, well, we got a drag force, and we also have the weight in newtons of the stone we're trying to launch. So we'll take the weight in newtons of the stone plus the force from the drag. We'll add that. 0.265 newtons. And we'll multiply this times the height. So that's our potential H. This is mg. So that's potential final. And final velocity, that's going to be 0. That's when the rock has went as high as it's going to go and getting ready to come back down. So let's just write this, what we got again. 1/2 m 20 squared is equal to, well, we may as well add these two. 5.29 plus 0.265 5.29 plus 0.265 equals 5.56 times h. Well, now we can solve for h. So h is going to equal 20 squared is 400 times 1/2 is 200, which would give me the mass, which is 0.54 kilograms. We got that mass from 5.4 kilograms by dividing 5.29 by 9.8, and that's going to give us 0.54 kilograms. So we got 0.54 kilograms times 200. That's from 400 times 1/2, give me that 200. And on the bottom, I'll have 5.56. So H is equal .54 times 200. That's 108 divided by 5.56 divided by 5.56, and that's equal 19.4 meters. So that's part A. So B is asking what is speed just before it hits the ground. Well, we know that since it's falling, the drag force is going to be in that direction. And of course, this is mg in this direction. So what we have is when we launch the stone, the drag force and the direction of the stone were in the same direction. So we add them. So in this case, the stone is coming back down, the drag force and mg are in opposite direction. So we're going to subtract one from the other. All we're interested in is the difference. So the difference between the drag force and this 5.29 would be 5.29 minus 0.265 will equal 5.025. So that's the difference in them. So I can just take this and plug it into this formula, this difference, and they want to know V. So we'll solve for that. So we'll start off. Well, MGH initial Well, we're going to have a value for that. It's going to be 19.4 meters plus 1/2 mv squared initial. Well, that's going to equal 0. We're at the top of it. The stone is as high as it's going to be, and it's getting ready to turn around and come back, which is going to equal mgh final. Well, it's going to hit the ground, so that's going to be 0 plus 1/2 mv square final. That's what we're looking for. So we got a little correction here. This value goes right here. This subtracted from that. So that's going to be 5.02 times h. And we know what h is, so we'll go 5.02 times h, which is 19.4, is equal to 1/2 mv square. So v square is going to equal 2 times 5.02 times 19.4 divided by m, which is 0.54. So v is equal to square root 2 times 5.02 times 19.4 divided by 0.54. So this is going to equal, if you do all the work, it's going to equal to 18.99 meters per second, which is approximately 19 meters per second. So part B, we realized that the difference between the drag and the force of the stone coming down, we did that. This is the difference between it. Came out to be 5.025. Then essentially we used the same formula that we had before with h, which we knew. And that's right here. Here's h, which we know, times that difference, 5.02, which equals 1/2 mv squared. And then we just solve. And we got v is equal to 19 meters per second. So that's all for that problem.